All right, welcome to section 5.1. We're going to be looking at graphing polynomial functions based on their characteristics. So first, our polynomial function p of x is we want our terms to have our powers in descending order with the constant at the end. It's important to understand that your powers must be positive integers. All right, so we should put right above this n is a, right here, positive integer. We don't want negative powers because then we're putting x's in the denominator. So a polynomial function never has x in the denominator of the term. So characteristics of our polynomial function is we're going to be talking about the degree of the polynomial. This is the largest power on x. If we put your terms in descending order, then this should be from your first term. So we call it an nth degree. Next, we're going to use the leading coefficient test to determine the left and right hand behaviors. So when I talk about left and right hand behavior, we're talking what does the left hand side of the graph look like? What is the right hand side doing? So as my x's approach negative infinity, is my graph going up or is it going down? As my x's approach positive infinity, is my graph going up or is it going down? Your turning points, these are your vertices, just like we talked about with relative mins and relative maxes. Those are your vertices, or turning points. Multiplicity of a zero, or zeros are technically called x-intercepts. Multiplicity means how many times an x-intercept repeats itself, and it shows that in the graph. And then we're going to talk about the y-intercept, which we already know, that's 0, comma c. So if you put 0 into all those x's, only thing you're left with is c at the end. All right, so talking a little bit more about our leading coefficient test. All right, this is for power functions. That means polynomial functions. What we're really going to look at here is just the first term and the last term of a polynomial function. Everything in between, nothing. Doesn't tell us much. So when you have a degree of n, the first term's power is even. When you look at your left and right hand behavior, as my x's go out to negative infinity, and you take negative x's and you raise them to an even power, you get positive y's. And of course, as we go out to positive infinity to the right, our x's are positive, so positives raised to an even power, still positive. Now, if your a is positive, then we're always going to be going up. Think of a parabola, if you will. All right? X to the second power, a is positive, it opens up. That would be true if it's x to the fourth, x to the sixth, x to the eighth. And if we make our a negative, which means it's less than 0, then our left and right hand arrows here will flip over the x-axis. That's a reflection transformation. So again, as x's are negative, you raise it to an even power, it becomes a positive value. And the only way it becomes negative is because a is negative, and now we're opening down. If we look at our n being odd, x to the first, x to the third, x to the fifth, then you're going to have a left and right hand behavior where the left side goes down. All negative x's raised to an odd power will be negative. Multiplying a positive a is not going to change anything. It's going down, negative y's. Positive x's raised to an odd power is positive, multiplied by a positive a still goes positive. And if a is negative, then again, we flip it over the x-axis. So if we have a negative x raised to an odd power, it's negative, but then multiplying it by another negative from your a makes it into a positive. And all your positive x's raised to an odd power, then multiplied by a negative, is going to go down. What's really important in these two left and right hand behaviors based on even powers and odd powers is notice that the right hand behavior for both of these functions are exactly the same. And we are going to exploit that when we go to graphing polynomial functions. So based on what we want to graph to the right-hand side as x goes out to positive infinity, we know that just looking at the sign of the first term, if a is positive, we know our graph goes up. If our x is to the first, or excuse me, x to the nth power, our first term, we have a negative, then we know it's going down. Now what the author is going to do is he is going to give you this notation. So as I was explaining this, as x approaches negative infinity, that means we're going to the left with our x's. Then the limit as x goes to negative infinity of your p of x, and p of x is your y coordinates. What are your y coordinates doing? Are they going to positive infinity or are they going to negative infinity? That's what they're asking us here. If the limit of our function p of x as x goes to positive infinity, what is our y's doing? And that's basically just reading, for again, going to the right as you go to positive infinity, that's just reading the sign off of your first term. If it's negative, you can say it's going down to negative infinity. If it's positive, it's going to positive infinity. But if you're going to negative infinity, you've got to stop and think, what's the power? And then what's the sign to decide what's happening over here, because they are different. Turning points. Two concepts that we need to know about turning points are those vertices. Number one, the most turning points a polynomial function can have is n minus 1. Again, n is your leading power. So if I had a fifth degree polynomial, 5 minus 1 is 4. I can have at most 4 turning points. If I had x to the sixth power, 6 minus 1 is 5. I can have at most 5 turning points. And number 2 uses the first concept. What's the most you can have? And then what are the other possible turning points that you can have? Well, you don't have 5, 4, 3, 2, 1 if your n is a 6. Your turning points can be reduced by 2 and only 2. And you keep reducing by 2 until you reach a 1 or a 0. This is based on odd multiplicity, which we're going to look at in a second, of 3 or higher. So for my example, if I had p of x, here's my polynomial function, it's x to the fifth power for my leading term. So number 1, at most I can have 5 minus 1, 4. Number 2, take that 4 and start subtracting a 2 from it. So the possible turning points would be the 4, and 4 minus 2 is 2, and 2 minus 2 is 0. So these are the 3 possible turning points of this function. Now, which one do you think I'm going to ask you on a test? Well, it's probably not going to be number 1. It's going to be number 2, because you have to know number 1 to start off number 2. So this part right here, put an asterisk by number 2, that's on the test, because it covers both of them. If we had x to the sixth minus x squared minus 1, again, looking at just the first term, n is a 6, that's my power. Subtract the 1 from it, 5. That's the most I can have. And now take that 5 and start subtracting 2. 5 minus 2 is 3. 3 minus 2 is 1. Stop. If I said 1 minus 2, I would have negative values. You can't have a negative number of turning points. So those are the possible turning points I can have. All right, multiplicity. You can have even multiplicity and you can have odd multiplicity. And I'm going to use a graph from my graphing calculator to help demonstrate this, because we will be graphing these crazy big huge polynomial functions, and we have to look at the graphs to get an idea of what's going on. Now we know, come back here, we know that if I graph x squared, it's a parabola. The vertex is at the origin. And what I'm going to graph next is x to the fourth, another even power. Now watch what happens to my graph. It's going to be a darker line. And what I really want you to focus in on is what's happening at this x-intercept between those two graphs. If you look at x squared, and I know I've blown this up a bit, but it almost looks as if I come down from the left and I just touch the x-axis and I head back up. I really don't cross the x-axis. I just touch it and go back up. And it looks like you kind of flatten out here with these little square pixels on the graph. And that's a hint that you have even multiplicity. So my x equals 0 for my x-intercept, it occurred twice at that point. So that x-intercept occurred twice. Now, when we go to x to the fourth, notice now that little flat line near 0 is a little bit wider. So that tells me that it's going to be bigger than x squared. It's a short flat line. This is a little bit longer of a flat line. And so that means x equals 0 4 times at that spot. Now if I go x to the sixth, it's going to be just a little bit longer. But you're not going to really see a polynomial function x to the sixth and have additional x-intercepts. So what happens here is that your x's are so small, like 0.1. But if you take 0.1 and raise it to the fourth power, that's 0.0001. That's so small that it doesn't get off the x-axis and the calculator puts it still at 0. Until you get to a value big enough that generates a value to start seeing or getting off of the x-axis for its graph. Odd multiplicity, here's y equals x to the first, a straight line, and y equals x cubed. Notice both of these graphs go through the origin. These are called go-throughs. They cross the x-axis. So again, touch and go if you have even multiplicity. Go-throughs if you have odd multiplicity. They cross the x-axis. But again, you get this same relationship. If x to the first, there's 1, it's a straight line going through. But now x to the third, notice again, here's the flat line right there. When you see that flat line on your graph, you know you have multiplicity. Does it go up? Is it a touch and go, even, or is it a go through? If it's a go through, then there's 3 x-intercepts at that point. And if we go x to the fifth, you can see it's just slightly longer. There's my x to the fifth, and there's that horizontal segment, just a little bit longer. So even multiplicity always does a touch and go. It never crosses the x-axis. Odd multiplicity always crosses the x-axis. And those are our characteristics of our polynomial function that's going to help us to graph.